want to know why is dimension like important. So in data science, it's knowing the dimension means that we know the intrinsic property of an object that regardless of the space it embedded in. And so what is a dimension? A dimension in mathematics is a point, and when we enlarge it by 3, it's still 1 point. So 1 equal to the 3 to the power of 0, and so we say the dimension of a point is 0. And for a line, we enlarge it by 3, there are 3 lines which equal to 3 to the power of 1, so we say a line has a dimension of 1. And by doing the similar process for the squares and cubes, we get that the square has a dimension of 2 and the cube has a dimension of 3. And so let's look at some more fun data sets. Those are 2 examples of the self-similar data sets, which if you zoom into them, they have a similar pattern to themselves. And the one on the left, it's called the Sierpinski triangle one, which you take a triangle and you cut the edge in half, and then you take away the small triangle in the middle. And so we'll say that when we scale a triangle by 2, we have 3 pieces of triangle. And the one on the right is called Cantor set, is that we take a line and we cut into 3 pieces, and we take away the middle part. And so we'll say that scaling a line by 3, we get 2 lines left. And so you may wonder what are the dimensions of those data sets. And
well, yeah, if anybody was screaming, take the log, and you're right. For sets with this nice self-similarity property, we may define this dimension by taking the log of sort of the number of copies that we have here and the factor which we scale it. So when we scale this one triangle by 2, we get 3 copies of itself. However, this definition is very restrictive as it relies on the self-similarity property of those data sets. However, mathematicians have realized that we can still define more rigorously the dimension of a data set by observing the change in scale when we cover the data set with these sort of special coverings. And we can think of these special coverings as either measuring our set with a single separate ruler. So as you see here, we have uniformly long squares, and we sort of observe how the number required to cover our data set changes as we shrink this ruler. And the other type of covering we could have is more like a measuring stick, where we have sort of this maximum length set that we can cover our overall set, but we can also sort of make these little smaller, finer coverings around these like smaller points. But then why do we care about studying this? I mean, we did just say that the dimension of a point is 0, so the dimension of a finite set is going to be 0. However, as you can see here, we have this this set that looks very, very similar to the Sierpinski triangle that we showed earlier, and it was generated using a chaos game. So we only have a discrete number of points, but it looks very, very similar to our Sierpinski triangle. And researchers, including ourselves, have noticed that if we zoom in on a point and sort of draw this circle around it, a ball, a box, whatever you want, and measure sort of how the number of points changes as we shrink the ball, we can actually calculate a number that is identical to the dimension of the continuous object that we had before. So from just this, I think we had 30,000 points here, we were able to calculate the same dimension number that we did as if we were to take the log 3 over log 2 of the original Sierpinski triangle. But then how can we generalize this so that we could apply it to whatever data set we have? That's the question that I want to answer.
Yeah. Drawing from all of these ideas that Javi and Linda has talked about, we defined a new definition of dimension that we call the Frostman dimension that we can use to approximate to the dimension of finite point sets. In order to understand that, we first define this local Frostman energy, which is this equation over here. I know it probably doesn't make a lot of sense, but I will explain it in a sec. Sorry.
Nice.
All right. So in order to arrive at the Frostman dimension, let's first take 3 critical observations. So observation 1 is that, let's say you have a point set and you have a circle or a ball inside the set, then how many points are captured by this ball? Well, we can notice that in this ball, you capture around, in this particular case, pi r squared number of points. But we can also generalize this idea so that and say that the number of points captured by a ball of radius r is approximately proportional to r to the power of d, where d is the dimension of the set. And this is going to be the key to figuring out the dimension. And our observation number 2 is that this proportionality argument becomes more precise as our number of points increase, so as n goes to infinity. And observation 3 is that we notice that dimension is actually a local property, which means that the dimension of the same set in different locations can actually be different. For example, inside the square, the points have dimension of 2, but in the same set over here, you have dimension of 1. So in order to capture this kind of local property of dimension, we need our r to be small enough. In other words, we want our r to approach 0 as n approaches infinity. So drawing from all of these observations, we notice that in our formula for our Frossman energy, if we have our S over here to be equal to the correct dimension of the set, then the fraction would evaluate to constant times r to the power of s over r to the power of s, which is just constant. And for large values of s, the top grows faster than the bottom, so our energy goes to infinity, and vice versa. For small values of s, it goes to 0. So this way, we can define our Frossman dimension as the largest value of s, such that the Frossman energy does not go to infinity.
So if you haven't been convinced yet that our way of computing the dimension of a point set is the absolute best, we were also not convinced yet, so we wanted to check out some other methods of doing the same thing worked. And so we turned to the correlation dimension. And before I go into the definition of this other method, we wanted to first check out what we should expect for point sets of different dimensions. So this one I got a square, which we all know is 2-dimensional line, and Sierpinski, where we need 3 copies to make a Sierpinski triangle that's 2 times as big. If I'm gonna stretch a ball by twice as wide, I should pick up 2 times as many points because it's a 1-dimensional object. And for my square, I should pick up 4 times as many points, right? And then the same is gonna be for our Sierpinski triangle, but instead of 2 or 4, we're gonna pick up 3 because I need 3 Sierpinski triangles to make one that's twice as big. The other thing that the correlation dimension does a little bit differently is what happens if we look at this sort of amount of points I pick up when I grow a ball for every point, which is ultimately going to be looking at how many point pairs with distance r, distance less than r, as we grow our radius. And so that's exactly what the correlation definition does, or the correlation dimension does. For different radii, we check out how many point pairs have distance less than r, and we see how this exponent of amount of point pairs grows when we grow this ball size. And so if we want to isolate this dimension for a given data set, we just do some epic log funny business, and using the fact that proportionality just means it's multiplied by some constant, and the multiplying inside of a log means we can bring out the exponent and bring in addition, we notice that, hey, this looks an awful lot like a linear regression line, and that's exactly what it is. So all we have to do is compute a bunch of point pairs for a bunch of r, and then look at the log of the point pairs compared to the log of the radii, and we should see what that exponent is, and that slope for this equation will be an approximation for dimension, and that's hopefully what our method should look like in game 2.
All right. So I'll just go through some of the results really fast. The principal results that we find are that, when we look at synthetic data sets such as randomly sampled points from a square, the Sierpinski triangle, or the cosine of Britain, we find the desired results. We're looking at that orange line, we're looking for it to remain straight. And what we find is that the dimensions that we're looking for do match up. And, hold on, there we go. And this also allows us to do something called data set stratification. If you remember the correlation integral that Vlad just talked about, this allows us to look at the local dimension of points. For example, we have in the squares that we find that the dimension is 2, and in the line we find that the dimension is 1 roughly. So this allows us to better use methods such as principal component analysis, because we know what dimension we're trying to reduce down to. And then finally, we get to future steps, which is just to work with more data sets. We know the primary difficulty is that we don't know that the dimension is going to be right off the bat, but because it works for these synthetic data sets, hopefully it will work for real world data sets. Okay, thank you.